your code might take a long time to run and you just find yourself waiting a very long time to get a result. So in the deep learning era, I think the ability to perform vectorization has become a key skill. Let's start with an example. So what is vectorization? In the previous video, you saw a few examples of how vectorization, by using built-in functions and by avoiding explicit for loops, allows you to speed up your code significantly. Let's take a look at a few more examples. The rule of thumb to keep in mind is when you're programming your neural networks or when you're programming logistic regression, whenever possible, avoid explicit for loops. And it's not always possible to never use a for loop, but when you can use a built-in function or find some other way to compute whatever you need, it will often go faster than if you had an explicit for loop. Let's look at another example. If ever you want to compute a vector u as the product of a matrix A and another vector v, then the definition of a matrix multiply is that ui is equal to sum over j, aij, bj, right? That's how you define ui. And so the non-vectorized implementation of this would be, to set u equals np dot zeros, would be n by 1, and then, for I, and so on, for j, and so on, right? And then ui plus equals, aij times bj. So now this has two for loops looping over both I and j. So that's the non-vectorized version. The vectorized implementation would be the same. Say u equals np dot a comma v. And the implementation on the right, the vectorized version, now eliminates two different for loops and it's going to be way faster. Let's go through one more example. Let's say you already have a vector v in memory and you want to apply the exponential operation on every element of, say, this vector v. So you compute u equals a vector that's e to the v1, e to the v2, and so on down to e to the vn. So this would be a non-vectorized implementation, right? Which is that first you initialize u to a vector of zeros, and then you have a for loop that computes the elements one at a time. But it turns out that Python and NumPy have many built-in functions that allow you to compute these vectors with just a single call to a single function. So what I would do to implement this is import NumPy as np, and then what you can just call u equals np dot e to the v. And so notice that whereas previously you had an explicit for loop with just one line of code here, this v is an input vector, u is an output vector, you've gotten rid of the explicit for loop, and the implementation on the right will be much faster than the one needing an explicit for loop. In fact, the NumPy library has many other vector value functions. So np.log of v will compute the element-wise log, np.abs computes the absolute value, np.maximum computes the element-wise maximum, so you can take the max of every element of v with 0, v star star 2, this takes the element-wise square of each element of v, 1 over v takes the element-wise inverse, and so on. So whenever you're tempted to write a for loop, take a look and see if there's a way to call a NumPy built-in function to do it without that for loop. So let's take all of these learnings and apply it to our logistic regression gradient descent implementation and see if we can at least get rid of one of the two for loops we had. So here's our code for computing the derivatives for logistic regression. And we had two for loops. One was this one up here, and the second one was gradient descent implementation and see if we can at least get rid of one of the two for loops we had. So here's our code for computing the derivatives for logistic regression. And we had two for loops. One was this one up here, and the second one was this one, right? So in our example, we had n or nx equals 2, but if you had more features than just two features, then you need to have a for loop over dw1, dw2, dw3, and so on. To want to do it without that. And gradient descent. So here's our code for computing the derivatives for logistic regression. And we had two for loops. One was this one up here, and the second one was this one, right? So in our example, we had n or nx equals 2, but if you had more features than just two features, then you need to have a for loop over dw1, dw2, dw3, and so on. So it's as if there's actually a for j equals 1 to nx, dwj, gets updated, right? So we like to eliminate this second for loop. That's what we'll do on the slide. So the way we'll do so is that instead of explicitly initializing dw1, dw2, and so on to zeros, we're going to get rid of this and instead make dw a vector. So we're going to set dw equals np.zeros, and let's make this a nx by 1 dimensional vector. Then here, instead of this for loop over the individual components, we just use this vector value operation, dw plus equals xi times dzi. And then finally, instead of this, we will just have dw device equals m. So now we've gone from having two for loops to just one for loop. We still have this one for loop that loops over the individual training examples. So I hope this video gave you a sense of vectorization, and by getting rid of one for loop, your code will already run faster. But it turns out we could do even better. So in the next video, we'll talk about how to vectorize logistic regression even further, and you see a pretty surprising result that without using any for loops, without needing a for loop over the training examples, you could write code to process the entire training set. So pretty much all at the same time. So let's see that in the next video. We've talked about We've talked about how vectorization lets you speed up your code significantly. In this video, we'll talk about how you can vectorize your implementation of logistic regression so that you can process an entire training set, that is, implement a single iteration of gradient descent with respect to an entire training set without using even a single explicit for loop. I'm super excited about this technique, and when we talk about neural networks later, without using even a single explicit for loop. Let's get started. Let's first examine the forward propagation step of logistic regression. So if you have m training examples, then to make a prediction on the first example, you need to compute that, right? Compute z using this familiar formula, then compute the activation, let's compute y hat on the first example. Then to make a prediction on the second training example, you need to compute that. Then to make a prediction on the third example, you need to compute that, and so on. And you might need to do this m times if you have m training examples. So it turns out that in order to carry out the forward propagation step, that is to compute these predictions on all m training examples, there is a way to do so without needing an explicit for loop. Let's see how you can do it. First, remember that we defined the matrix capital X to be your training inputs, stacked together in different columns like this. Right? So this is a matrix that is a nx by m matrix. So I'm writing this as a Python NumPy shape, but this just means that x is a nx by m dimensional matrix. Now, the first thing I want to do is show how you can compute z1, z2, z3, and so on, all in one step. In fact, with one line of code. So I'm going to construct a 1 by m matrix. This is really a row vector, where I'm going to compute z1, z2, and so on, down to zm, all at the same time. It turns out that this can be expressed as W transpose, the capital matrix X, plus, and then this vector, B, B, and so on, B, where this thing This b thing is a 1 by m vector, or 1 by m matrix, or that is a m-dimensional row vector. So depending on how familiar you are with matrix multiplication, you might see that W transpose x1, x2, and so on through xm, that W transpose is going to be a row vector, right? So this W transpose will be a row vector like that. And so this first term will evaluate to W transpose x1, W transpose x2, and so on, dot, 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 W transpose xm. And then when you add this second term, b, and so on, you end up adding b to each element. So you end up with another 1 by n vector, where that's the first element, that's the second element, and so on, and that's the nth element. And if you refer to the definitions above, this first element is exactly the definition of Z1, the second element is exactly the definition of Z2, and so on. So just as X was what you obtained when you took your training examples and stacked them next to each other, to be this, where you take the lowercase z's and stack them horizontally. I'm going to define capital Z to be this, where you take the lowercase z's and stack them horizontally. Okay, so when you stack the lowercase x's corresponding to different training examples horizontally, you get this variable capital X. In the same way, when you take these lowercase z variables and stack them horizontally, you get this variable, which I'm going to denote via capital Z. And it turns out that in order to implement this, the numpy command is capital Z equals np dot w dot t, that's W transpose X, and then plus B. Now, there is a subtlety in Python, which is that here, B is a row number, or if you want, is a 1 by 1 matrix, so it's just a normal row number. But when you add this vector to this row number, Python automatically takes this row number B and expands it out to this 1 by m row vector. So in case this operation seems a little bit mysterious, this is called broadcasting in Python, and you don't have to worry about it for now. We'll talk about it some more in the next video. But the takeaway is that with just one line of code, with this line of code, you can calculate capital Z, and capital Z is going to be a 1 by m matrix that contains all of the lowercase z's, lowercase z1 through lowercase zm. So that was Z. How about these values, A, right? What we'd like to do next is find a way to compute A1, A2, and so on through AM all at the same time. And just as stacking lowercase x's resulted in capital X, and stacking means stacking horizontally, lowercase z's results in capital Z, stacking lowercase a's is going to result in a new variable which we're going to define as capital A. And in the program assignment, you see how to implement a vector valued sigmoid function so that the sigmoid function inputs this capital Z as a variable and very efficiently outputs capital A. So you see the details of that in the programming assignment. So just to recap, what we've seen on this slide is that instead of needing to loop over m training examples to compute lowercase z and lowercase a one at a time, you can implement this one line of code to compute all the z's at the same time, and then this one line of code with appropriate implementation of lowercase sigma to compute all the lowercase a's all at the same time. So this is how you implement a vectorized implementation of the forward propagation for all m training examples at the same time. So to summarize, you've just seen how you can use vectorization to very efficiently compute all the activations, all the lowercase a's, sort of at the same time. Next, it turns out you can also use vectorization to very efficiently compute the backward propagation, to compute the gradients. Let's see how you can do that in the next video. Backward propagation to compute the gradients. Let's see how you can do that in the next video. In the previous video, you saw how you can use vectorization
study music.
Instrumental study from Spotify.
Alexa, stop.
To compute the predictions, the lowercase a's, for an entire training set all sort of at the same time. In this video, you see how you can use vectorization to also perform the gradient computations for all m training examples, again all sort of at the same time. And then at the end of this video, we'll pull it all together and show how you can derive a very efficient implementation of logistic regression. So you will remember that for the gradient computation, what we did was we computed dz1 for the first example, which is going to be a1 minus y1, and then dz2 equals a2 minus y2, and so on. And so on for all m training examples. So what we're going to do is define a new variable d capital Z, which is going to be dz1, dz2, right, dzm. Again, all the d lowercase z variables stacked horizontally, so this would be a 1 by m matrix, or alternatively a m-dimensional row vector. Now recall that